All right, let's get right into this explainer. Picture this. You're driving a brand new electric vehicle right through the middle of the desert. There's not a cell tower in sight for miles, yet the car still knows exactly where it is, down to the centimeter. How? Well, we're currently looking at a profound structural shift in automotive design. The newest electric vehicles, specifically those being exported globally from China, are rapidly integrating satellite connectivity directly into their hardware. And this isn't just some flashy gimmick. It's a foundational change driven by the absolute need for remote global connectivity, highly precise positioning for autonomous driving, and ultra-reliable data links.
To really understand this shift, we first have to ask a pretty critical question. What actually happens when a heavily software-defined car just loses its signal? As modern vehicles evolve into what are basically highly advanced computers on wheels, their core functionalities, we're talking navigation, battery management, even self-driving systems, they all depend entirely on a constant, unbroken stream of data. So how do these intelligent machines survive in regions where standard cellular networks just completely fade away?
Just to give you a sense of the sheer scale we're dealing with here, look at this. Over 16.4 million T-boxes, which is the hardware that connects cars to standard ground-based cellular networks, were installed in China's passenger car market in 2023 alone. That's a massive 78% installation rate. So terrestrial connectivity hardware is already standardized. The real challenge now is pushing that connectivity way beyond the limits of cell towers and linking directly up into orbit.
Here is our roadmap for today's explainer. We'll start with the connectivity dead zone, move into precision for autonomous driving, then cover always-on software updates, emergency rescue, and lifelines, and finish up with the geopolitical security divide.
Starting with Section 1, the connectivity dead zone, escaping the limits of terrestrial networks.
Think about your last major road trip. It turns out standard cellular networks actually only cover about 60% of the Earth's land area. That leaves some massive signal blind spots in deserts, mountains, and really remote regions. And as millions of these highly computerized vehicles start driving into fragmented global networks, ground infrastructure alone just isn't enough to keep their data flowing. Every time they cross a border, it disrupts local telematics services, and losing that continuous data link, well, that's a massive operational risk.
Moving on to Section 2, Precision for Autonomous Driving, focusing on the Level 3+ autonomy factor. You see, high-level autonomous driving requires a car to know its exact footprint on the dynamic roadway in real time. Enter the Beidou 3 navigation satellite system. This is a Chinese fleet of 30 active satellites that feeds highly precise spatial corrections straight down to the vehicle. While standard GPS is great for general routing, advanced autonomous systems absolutely rely on these specialized networks just to function safely.
The difference in safety here is literally game-changing. Standard GPS gives you accuracy within several meters. That's totally fine if you just need to know you're on a certain highway, but it is super dangerous if a computer is trying to weave through dense urban traffic. Beidou 3 RTK algorithms shrink that margin of error down to millimeter to centimeter level precision. It knows exactly where the physical paint on the lane ends, which makes advanced driver assistance systems so much more reliable.
And to process all this data in real time, automakers aren't even waiting on the traditional tech giants. Chinese semiconductor firms are achieving full-stack autonomy by building these specialized automotive-grade satellite chips directly into the car's hardware. We're seeing triple-frequency AI error correction chips and even radiation-hardened processors turning everyday sedans into incredible spatial mappers.
All right, Section 3, always-on software updates, and how they are securing the over-the-air data link. Software-defined vehicles obviously need constant over-the-air or OTA updates, but imagine your 5G drops right in the middle of a critical system update. You could literally brick the car's computer. To prevent this, these cars use a brilliant dual-box architecture. If the terrestrial T-box loses its signal, it instantly hands the data stream over to a dedicated satellite S-box, keeping that update downloading safely from orbit without a single interruption.
And this fail-safe isn't just a luxury, it's actually driven by some incredibly strict new regulations. In the past, companies might push silent updates that sneakily reduced battery range to manage thermal hazards. But starting in 2026, defect updates are legally classified as product recalls. Dropping a connection during a mandated recall update is a huge liability, making this unbreakable satellite link an absolute legal necessity.
When you look at the orbital infrastructure supporting all this, the scale is pretty mind-blowing. Geely is launching thousands of low Earth orbit satellites for brands like Zeekr and Polestar. BYD is tapping into geostationary networks. Then you have state-owned constellations targeting up to 13,000 satellites. Essentially, the auto industry is starting to colonize commercial aerospace.
Which brings us to Section 4, Emergency Rescue and Lifelines, using this as survival technology in extreme environments.
Beyond just managing software, this ground-to-orbit link provides a literal lifeline. Take the BYD Yangwang U8 luxury SUV, for instance. It utilizes a high-orbit satellite network with an antenna completely hidden right inside the roof, so don't need to step outside and manually point a dish at the sky. If you're off-roading and the airbags deploy, or the car is caught in a flash flood, it automatically fires off an SOS signal, maintaining a stable data link even while the vehicle is actively moving.
Now, Xiaomi takes a completely different, but honestly really clever approach. Instead of building all that heavy satellite gear into the car itself, the Xiaomi SU7 uses docked flagship smartphones as a bridge. It leverages AI neural networks to compress heavy diagnostic images so they can squeeze straight from the dashboard through narrow satellite bands that are normally reserved just for basic text.
Finally, Section 5, the geopolitical security divide, looking at invisible borders and data governance.
The crucial point here is that integrating aerospace capabilities into commercial exports has created a profound global security divide. As these hyper-connected EVs enter Western markets, they are being heavily scrutinized. International security agencies and legislators are increasingly viewing these vehicles through a lens of potential risk, explicitly referring to them as surveillance platforms on wheels.
We're observing a reality where the fusion of advanced driving platforms and satellite links has triggered immense regulatory pushback. There are real anxieties out there over high-bandwidth external telemetry and the possibility of vehicles mapping sensitive critical infrastructure down to the centimeter. As a direct result, we're seeing the establishment of robust cybersecurity firewalls in Western markets, creating a fractured, completely bifurcated global supply chain based entirely on where data originates and how it gets routed.
So that leaves us with a massive question to ponder. As the automotive and aerospace industries permanently fuse together, how will the world adapt to this bifurcated future of space-connected mobility? Navigating the invisible borders of this new digital frontier is going to be incredibly complex, and it's a space we will definitely be watching very closely.